Hello everyone, I'm Enrique Sierra from the University of Burgos, and I'm going to present the article Wind Turbine Pitch Control with an RBF Neural Network. This is the outline of the presentation. First, the problem will be introduced, then the mathematical model of the wind turbine will be presented. After this, the architecture of the neural controller will be presented, and the simulation results will be shown. The conclusions and the future works will end the presentation. Wind turbines harvest the wind resource to generate clean energy. It's one of the most used clean energy due to high efficiency and good payback. The generating capacity of the wind turbines depends on the wind speed and also depends on the size of the blades, of course. There are different control actions in a wind turbine. First is the generator speed. In the generator speed, this control is performed from the cut-in speed to the rated output speed, and here the aim is to track the optimum curve to maximize the power that we are getting. And also it's possible to control the angle of the blade. This is named the pitch control. This is normally performed from the rated output speed to the cut out speed, and here the aim is to stabilize the power around the rated power. And the last control action possible is to control the rotation of the nacelle. This is the yaw control, and here the target is to align the nacelle to the main wind stream. In this article, we are going to focus on the pitch control in this region. We are going to work in this region. This is not easy due to the high nonlinear dynamics. Also, due to the internal variables are very coupled, there are unknown parameters, and on top of that, it's subjected to random external conditions such as wind, the weather. These problems are even more critical, especially critical for floating offshore wind turbines due to the harsh environment conditions that they produce vibration and fatigue. These problems make the artificial intelligence, like artificial neural network techniques, as a promising approach for the identification and the control of these complex systems. This equation represents the mathematical model of the wind turbine that has been implemented. It has two state variables. That is, the first is the current in the armature, and then is the angular speed. The equation of the current in the armature depends on the angular speed and the current armature, and it's possible to see that in this equation that the state variables are coupled, okay? And the current in the armature is also related, of course, with the inductance of the armature and the resistance in the load and in the armature also. By the other hand, the equation of the angular speed is divided in three parts. This is the first part, second, and third. The first part is related and the way how the wind is transformed to the mechanical power, and is related to the pitch angle. This is the pitch angle, and the wind speed. The second part is related to the current in the armature, and the last part is related with the angular speed also. At the end, the output power is directly related with the current in the armature. This figure describes what is the architecture of the neural controller, what has been implemented. First of all, the reference for the power, or the rated power, less the output power of the wind turbine, generates the error power. The error power and its derivative goes to a saturator, and it generates the saturated error power and the saturated of the derivative of the error power. They feed the inputs of the RBF neural network, and the RBF neural network generates the reference for the pitch control. This reference for the pitch control goes into a bias. This bias is used because the range of the pitch control is from 0 degrees to 90 degrees, and this bias is situated in the middle of this range. Okay, this reference for the pitch control is also saturated to avoid we are below or over these limits. And then here we have what is the reference for the pitch control that is introduced to the wind turbine. This RBF neural network has several weights, and these big weights, are updated by a learning algorithm. This learning algorithm, what is used to update these weights, is the saturated error power information that it comes from here. The main equation related to the calculation of the RBF are shown in this slide. First, the output of the RBF neural network is calculated as the addition of some exponential functions weighted by the weights of each neuron. The distance in each neuron is calculated by this function, what computes the distance from the center of the neuron to one point composed by the saturated error and the saturated of the derivative of the error with this way. And this distance is normalized, as is possible to see in the equation. The weights of the neural network are updated by this learning algorithm. The equation is the equation of the learning algorithm. It's possible to see how the exponential function is exactly the same that is used to calculate the output of the RBF. And the difference from the other learning algorithm is that we are substituted this part. Normally in a supervised learning, what we have here is the error between the target and the output of the RBF. As we don't have any labeled data to be used in the supervised learning, we have to use unsupervised learning. And we are substituting this part by the saturated error power. This is one of the main contributions of this paper. The comparison of the power when different control strategies are applied is shown in this figure. The blue line is the power that we have when we fix the angle to 0 degrees. The red is when we fix the angle to 90 degrees. The purple line is the output power that we have when we apply the neural controller, and the yellow one is when the PID is applied. It's possible to see how the performance of the neural controller is much better than the PID controller. The error is less, and also the overshoot is less. In this table, it's also possible to observe the same results that we have seen in the previous figure. Regarding the error is less, and also the overshoot is less. In addition, the settling time is a bit less than when the RBF is applied, respecting that the PID is applied. To summarize the work, a first approach of an online neural control for the pitch angle of a wind turbine has been presented. This neural controller uses unsupervised learning because of the neural network is not pre-trained, but it learns online from the system. The simulation results validate the effectiveness of this controller to stabilize the output power, even with changing wind conditions. And also it has been compared with a PID controller with good results. As main future work lines, we can highlight we are going to focus on the control on the rotor speed, and also we'll study the influence of the pitch control in the vibration and the mechanical loads of the wind turbine, because it's a very important point for the offshore wind turbines.